In this lab, we observed an object moving at a constant velocity and compared it to a model of an object moving at a constant velocity. This comparison explores Newton's laws of motion, specifically the first law, which states that objects in motion tend to stay in motion and objects at rest tend to stay at rest unless acted upon by an outside force. Whether or not our observations match the model is important because it confirms this long-standing law of physics with a real-world replicatable example. And so if we go to the tracker and we take a look at the data first, you'll see that the velocity over time graph here it has quite a bit of deviation. It has a little bit more towards the beginning here and a spike towards the end as well. But overall it's staying between this 0.2 and 0.16, so it's around 0.2 deviation from the middle here. And then even the outliers are only like 0.04 away. So it's not a whole ton of deviation. When we look at the position versus time graph, you can see that the slope seems to be constant throughout the whole thing. And so you'll see that the reasoning for these spikes, when I run the tracker, you'll see that the reasoning for these spikes is because obviously I am not a robot, and when I manually inputted the positions of this, I did not every single time put it perfectly on the axis. I didn't every single time put it perfectly in the middle of the cylinder. I am not a robot, I'm a human. So there's naturally going to be some human error when I'm doing this manually. And my auto tracker, which probably would have got more accurate results, was not recognizing this object. So we work with what we got. And you'll see when I run it that it follows these graphs, the data follows, and so far looking like we're upholding Newton's first law of motion. Now if we go to the model, you'll see my code, and you'll see there is no net force. The net force is equals 0. And so when I run the program, you'll see that there is a constant slope. The velocity versus time is constant, it's horizontal, it's perfectly on that 0.175. There's no deviation because there's no human error. It's a perfect environment. And so when we compare the model of the observed position over time and the simulated position over time, you'll see that actually the lines match up quite well. The blue is the observed position, the orange is the model position, and the only real deviation is this beginning part where it goes a bit above, and this end part where it goes quite a bit above, and some little ones in between. And when we go back to the tracker, we'll see that this is actually where the velocity over time graph spiked, which, as I explained before, is most likely due to human error because objects don't just randomly increase velocity and decrease velocity without any force acting upon them. So it looks like overall, at a glance, we're upholding Newton's first law so far. But what if I change this axis? What if I, let's say, switched it, put the axis all the way over here, made it negative, right? Well, then we would have a bit of it would be the same. It would be exactly the same. You see it goes from nearly the end to the beginning, and the velocity over time is the same. This graph is not really changing at all. The position over time graph still looks relatively straight. The only thing that would slightly change it probably is if I decided to turn it for some reason, which you see is, but there's no reason to do that. So great, the observations are predicted quite well by the simulation. So what does this mean? Well, it means that Newton's first law is upheld. There's no net force on this object. Or if there is, it's very slight. And yeah, we're upholding Newton's first law. Great. Thank you.